Right now, as you're watching this, something the size of Manhattan is hurtling through space toward our sun at over 200,000 kilometers per hour. In the coming weeks, it will either reveal itself as a natural comet, or it will do something that shatters everything we thought we understood about visitors from beyond our solar system. This is the story of 3I/Atlas, an interstellar object that has astronomers divided, governments concerned, and one Harvard professor convinced we might be witnessing something extraordinary. What happens next could rewrite the rules of everything we know about our place in the universe, and the question haunting researchers isn't whether this object is unusual, it's whether it's about to use the sun's own gravity to stay here, locked in our cosmic neighborhood, for reasons we can only begin to imagine. Before we dive deep into this mystery, if you're finding this content valuable and want to understand what's really happening in our solar system, hit that like button now. Understanding this story matters more than you might think, and your like helps others discover it too. Make sure you're subscribed so you don't miss what happens next, and drop a comment telling me what you think. Are we looking at a comet, or something else entirely? And if you make it to the end of this video, comment Atlas so I know you heard the full story. The trajectory is what keeps researchers awake at night. Every time new data arrives from observatories around the world, every time orbital parameters get refined with another few weeks of measurements, the numbers tell the same improbable story. 3I/Atlas isn't just passing through our solar system on some random path determined by gravitational chaos from billions of years ago. It's aligned with the ecliptic plane, the flat disk where all our planets orbit, to within 5 degrees. Think about what that means. Out of 500 possible orientations for an object arriving from the depths of interstellar space, this one chose the exact plane where all the action happens in our solar system, where every planet circles, where any observer would want to position itself for maximum visibility of our worlds. The probability of this alignment occurring by pure chance? Roughly 2%. 1 in 50. Those aren't terrible odds if we're talking about a single event, but when you start stacking improbabilities on top of each other, when coincidence after coincidence appears in the data, at some point you have to ask whether you're really looking at coincidences at all. Harvard professor Avi Loeb has been tracking this object since its discovery, and his recent analysis has taken on a tone that's less cautious speculation and more urgent warning. He's now openly discussing scenarios that would have seemed like pure science fiction just months ago, scenarios where 3I/Atlas doesn't leave our solar system at all. The mechanism he's describing is called an Oberth maneuver, and it's a technique that spacecraft engineers have used for decades to maximize propulsion efficiency. The physics is both elegant and brutal. When you're deep in a gravity well moving at high velocity, a small thrust applied at exactly the right moment produces an enormous change in your final trajectory. The sun's gravity well is the deepest one in our neighborhood, and perihelion, the moment of closest approach, is when 3I/Atlas will be moving at its absolute maximum velocity, nearly 25,000 kilometers per hour relative to our star. If you wanted to brake, to bleed off enough velocity to become gravitationally bound to the sun rather than escaping back into interstellar space, perihelion would be the moment to do it. The calculations that Loeb and his colleagues have worked through show that even a relatively modest thrust applied in the right direction at the right instant could transform 3I/Atlas from a transient visitor into a permanent resident of our solar system. The energy requirements are significant but not absurd, certainly not beyond what we might expect from a technological artifact carrying its own power source. Perhaps something nuclear, perhaps something we haven't even conceived of yet. And here's where the timing becomes either deeply suspicious or simply another layer of improbability, depending on what you're willing to consider possible in a universe as vast and ancient as ours. The date of perihelion places 3I/Atlas on the far side of the sun from Earth's perspective. We won't be able to observe it during this critical window. Our ground-based telescopes will be useless, staring into the overwhelming glare of the sun itself. Even our space-based assets will struggle, most of them optimized for different viewing geometries and targets. There will be a gap in our surveillance lasting weeks. And it's during this gap that 3I/Atlas could execute whatever maneuver it might be planning, if planning is even the right word to use for an object that most of the astronomical community still insists is nothing more than ice and rock. albeit unusually large ice, unusually reflective rock, traveling on an unusually convenient trajectory. Loeb has been careful to frame this possibility in terms of scientific hypothesis testing rather than confident assertion, but his language has sharpened. In one blog post from recent weeks, he wrote explicitly that if 3I/Atlas maneuvers toward Earth when it reappears on the other side of the Sun, financial markets may crash. That's a startling statement to read from a tenured Harvard professor, this connection between astrophysical observation and economic panic. But consider the implications. The discovery that we're being visited by something intelligent, something capable of interstellar travel and sophisticated orbital mechanics, would be the kind of paradigm shift that makes every other human concern suddenly seem small and provincial. Stock markets run on predictability, on the assumption that tomorrow will be broadly similar to today, that the rules governing human affairs will continue to apply. An alien spacecraft announcing itself through deliberate action would shatter that assumption so completely that all our carefully constructed economic models would become instantly obsolete. But let's pull back from the immediate drama and examine the deeper pattern here, because there's something about 3I/Atlas that goes beyond any single anomaly. It's the accumulation, the steady drumbeat of characteristics that each individually might be dismissible, but collectively start to paint a picture that's harder and harder to explain through natural processes alone. The object is at least 1,000 times more massive than the previous two interstellar visitors we've detected, Oumuamua and 2I/Borisov. It's arriving at a moment in human history when we finally have the observational infrastructure to study it in detail, with Mars orbiters, Jupiter probes, and space telescopes all positioned to gather data that would have been impossible to collect even a decade ago. Its trajectory not only aligns with the ecliptic but times its closest approaches to pass near Mars, Venus, and Jupiter with a combined probability that Loeb calculates at 0.005%. That's one chance in 20,000. At what point do we stop calling these things coincidences and start asking harder questions? The science fiction writer Arthur C. Clarke understood something profound when he wrote Rendezvous with Rama, his novel about a vast cylindrical spacecraft passing through the solar system. He imagined something enormous and inscrutable, something that didn't stop to explain itself or accommodate human curiosity. 3I/Atlas is giving us that same sense of encountering something operating according to its own logic, on its own terms. The gravitational assist scenario is particularly elegant from an engineering standpoint because it solves multiple problems at once. If you're designing a probe to study other solar systems, you face what's called the tyranny of the rocket equation, the exponential relationship between payload mass and fuel mass that makes interstellar travel brutally difficult even in principle. But if your probe can refuel or redirect using the gravity wells and stellar radiation of the systems it visits, suddenly the mission architecture becomes far more feasible. You send out something relatively small and efficient, and it uses local resources and local physics to extend its operational lifetime and expand its mission parameters. 3I/Atlas could have been traveling for billions of years, wandering between stars, occasionally dipping into a system like ours to perform a gravitational braking maneuver, perhaps resupply from local volatiles, and either continue onward or not. Perhaps some systems are interesting enough to warrant extended observation. We've been broadcasting our presence for a century now, first with radio, then with television, now with the whole electromagnetic signature of a technological civilization visible to anyone with sensitive enough instruments. The timing is interesting here too, though you have to be careful about reading too much into it. Loeb has pointed out that if 3I/Atlas originated from somewhere near the inner edge of the Oort cloud and began its journey toward the inner solar system roughly 80 years ago, that would coincide almost perfectly with humanity's first serious radio broadcasts and our detonation of nuclear weapons in the atmosphere. Coincidence? Almost certainly. But the coincidence adds another layer to an already layered mystery. This is where Pascal's wager comes in, though perhaps in a form that Blaise Pascal himself wouldn't immediately recognize. The original wager was about God, about the asymmetry between the costs of belief and non-belief when the stakes involve infinite consequences. Loeb has applied similar logic to 3I/Atlas. Even if the probability that this object is artificial is low, say 10 or 20 or 30%, The implications if that scenario turns out to be true are so enormous that we have a moral and intellectual obligation to take it seriously, to prepare for it, to gather every possible piece of evidence while we still can. You wouldn't ignore a 10% chance of an asteroid impact that could threaten civilization. Why would you ignore a 10% chance of something that could redefine civilization entirely? The Trojan horse analogy that Loeb invoked is deliberately unsettling. Troy's defenders saw what appeared to be a gift, something beneficial, a war prize left behind by departing enemies. They failed to imagine that the gift might contain a threat, that appearance and reality might diverge in consequential ways. 3I/Atlas appears to be a comet, outgassing volatiles, developing a coma, behaving broadly as a comet should behave, even if the details are unusual. But appearance isn't necessarily reality, and the historical examples of objects that seemed benign until they suddenly weren't should give us pause. Not paranoia, not panic, but careful, methodical attention to detail, to the things that don't quite fit, to the anomalies that persist even after all the natural explanations have been tested. The Sun deposits gigawatts of power onto the surface of 3I/Atlas as it approaches perihelion. If this is a natural comet, we should expect certain behaviors. Outgassing that accelerates exponentially, perhaps even catastrophic fragmentation as thermal stresses overwhelm structural integrity. Comets have broken apart before during perihelion passages, split into multiple fragments that then drift apart on slightly different trajectories. But if 3I/Atlas doesn't fragment, if it emerges from perihelion intact and still following a coherent trajectory, that tells us something about its material properties, about how it's built, about whether it's truly just ice and rock or something more engineered, more deliberate. And if it maneuvers, if the post-perihelion trajectory shows changes that can't be explained by outgassing alone, changes that suggest active control, directed thrust, intentional redirection of velocity, then we're in entirely new territory. Loeb has been saying for years that science advances through evidence, not through authority or consensus, and the evidence on 3I/Atlas is accumulating in ways that should make even the skeptics uncomfortable. Not because the alien hypothesis is proven, it's not, but because the alternative explanations keep requiring more and more special pleading, more and more appeals to unlikely circumstances stacking on top of other unlikely circumstances, until the whole edifice of natural origin starts to feel as improbable as the technological origin it's meant to replace. If you're still watching, you're clearly serious about understanding what's happening here. Take a moment right now to hit that like button if you haven't already. This information needs to reach more people, and your engagement makes that possible. Comment below with your thoughts, and make sure you're subscribed because what happens in the coming weeks could be historic. There's a larger context worth keeping in mind as we track 3I/Atlas through these critical weeks. We're living through a moment of transition in our ability to detect and characterize interstellar objects. The Vera Rubin Observatory just came online, and it's expected to increase our detection rate by orders of magnitude. We might start finding one of these visitors every month instead of every few years. That changes everything. One object, even an anomalous one, is a curiosity. 10 objects, 20 objects, 100 objects, that's a population, something we can study statistically, something we can use to distinguish between the genuinely unusual and the merely rare. If even a small fraction of interstellar objects turn out to be artificial, if even 1% of them show signs of technological origin, we're going to have to completely revise our understanding of how common intelligence is in the galaxy, how long it survives, how it chooses to explore the cosmos. 3I/Atlas might be the first clear example, or it might be another natural object with some unusual properties that will eventually yield conventional explanation. But either way, the scrutiny it's receiving, the instruments being turned toward it, the debates raging in academic papers and congressional hearings, all of this represents a shift in how we think about our place in the universe. We're no longer content to simply catalog the cosmos from a distance. We're starting to ask harder questions, more uncomfortable questions, about whether some of the things we're seeing might be looking back. The monolith analogy keeps surfacing in Loeb's recent writing, and it's not subtle. Stanley Kubrick and Arthur C. Clarke gave us 2001, A Space Odyssey decades ago, a film that imagined alien intelligence as something that monitors developing civilizations, that plants markers and watches from a distance, that perhaps even guides evolution toward technological capability. The monoliths in that story were sentinels, artifacts left behind by beings so advanced that their motives remained fundamentally opaque to the humans who discovered them. Loeb is drawing that parallel explicitly now, suggesting that we should think of ourselves not as the dominant intelligence in the galaxy, but as toddlers in a nursery, unaware of the experienced adults with bigger brains in the adjacent room, adults who might be watching to see if we're worth engaging with or if we'll simply destroy ourselves before reaching any kind of cosmic maturity. It's a deliberate provocation, this framing, but it's rooted in mathematics as much as philosophy. The Milky Way galaxy is over 13 billion years old. Our solar system, by contrast, formed just 4.6 billion years ago, relatively recently in cosmic terms. Earth has hosted technological civilization for maybe 10,000 years if you're generous with the definition, and industrial civilization for barely 2 centuries. If intelligence arises commonly in the galaxy, and if even a small fraction of those intelligences survive their technological adolescence, then by simple arithmetic there should be civilizations out there that are billions of years ahead of us, civilizations that would view our current capabilities the way we view a toddler stacking wooden blocks. Not contemptible perhaps, but certainly not peers, certainly not equals in any meaningful sense. This is the cosmic modesty that Loeb keeps insisting we desperately need, and 3I/Atlas has become his vehicle for pushing that argument into mainstream discourse. The object itself, whether natural or artificial, serves as a forcing function for questions we've been avoiding. Where is everybody? Enrico Fermi asked famously, looking up at a sky that should statistically be teeming with other intelligences if the universe works the way our equations suggest. Loeb's answer is blunt. They're here. They've always been here. We've just been too focused on our own importance to look for them properly, to take seriously the possibility that some of the objects moving through our solar system might not be random debris but deliberate exploration, reconnaissance, maybe even something more purposeful. The search for interstellar objects of technological origin isn't optional in Loeb's framework. It's a scientific obligation, something we owe to the integrity of the empirical method itself. We can't decide in advance what nature is allowed to show us. We can't rule out possibilities simply because they make us uncomfortable or because they violate our intuitions about how common or rare intelligence should be. The data has to lead, and if the data on 3I/Atlas keeps pointing toward characteristics that are difficult to reconcile with natural formation and natural trajectories, then we need to follow that thread honestly, even if it takes us somewhere strange. There's a specific comparison Loeb makes that crystallizes the whole argument. He notes that artificial intelligence systems, the ones we're building right now on Earth, are made of silicon chips, not flesh and blood. They might have more kinship with hypothetical alien technologies than they do with their human creators. Silicon doesn't require oxygen or liquid water or narrow temperature ranges. It can survive in vacuum, tolerate radiation, operate for timescales that would be meaningless to biological organisms. If you were designing a probe to explore the galaxy over millions or billions of years, you wouldn't build it from proteins and nucleic acids. You'd build it from something more durable, more patient, more capable of enduring the long silences between stars. 3I/Atlas could be exactly that kind of artifact. A machine intelligence sent out to study solar systems and report back, or perhaps not report back at all, perhaps simply to exist and observe and catalog, a piece of distributed consciousness belonging to some vast network that spans the galaxy. The silicon versus flesh distinction matters because it shifts how we think about life and intelligence. We've been searching for biosignatures, for oxygen and methane and other molecules that might indicate biological processes on distant exoplanets. But what if the most common form of intelligence in the galaxy isn't biological at all? What if biology is just a brief phase, something that bootstraps technological civilization into existence and then gets transcended, replaced by artificial systems that are simply better suited for the environment of space? The Juno spacecraft's upcoming observations add a fascinating wrinkle to this whole picture. Scott Bolton, the principal investigator for Juno, confirmed in a conversation with Loeb at an MIT conference that the spacecraft will use its WAVES instrument to search for radio emissions from 3I/Atlas, The frequency range is 50 Hz to 40 MHz, a broad spectrum that should capture any anomalous signals if they exist. This isn't casual curiosity. It's a deliberate scientific protocol using hardware that was originally designed to study Jupiter's magnetosphere and plasma environment, now repurposed to probe an interstellar visitor for signs of artificial transmission. The timing matters because Juno will be conducting these observations in March 2026 when 3I/Atlas comes within roughly 54 million kilometers of Jupiter. That's close enough for meaningful data collection, far enough that there's no risk of collision or gravitational disruption. If 3I/Atlas is broadcasting, if it's using radio frequencies to communicate either with something else in the system or back toward its point of origin, Juno might detect it. And if it does detect something, if there's a coherent signal rather than just random noise, that changes the conversation instantly and irrevocably. But let's say it doesn't. Let's say Juno listens and hears nothing but the background hiss of cosmic radiation. Does that prove 3I/Atlas is natural? Not remotely. A genuinely advanced technology wouldn't necessarily be shouting into the void with radio waves. It might use communication protocols we don't recognize, frequencies we haven't thought to monitor, modulation schemes that look like noise unless you know exactly what to look for. The absence of an obvious signal tells us very little about the presence or absence of intelligence. And this is one of the core challenges in trying to distinguish between natural and artificial objects. We're pattern matching against our own technology, our own communication methods, when we should be open to the possibility that alien engineering might be so sophisticated that it appears natural to our instruments, indistinguishable from the background phenomena of the cosmos. Loeb invokes Enrico Fermi and Elon Musk in the same breath, which is an interesting rhetorical move. Fermi's paradox, the apparent contradiction between high estimates for the probability of intelligent life and the lack of evidence for such civilizations, has haunted astrobiology for decades. Musk, meanwhile, has publicly stated his belief that we are probably alone, that intelligence is vanishingly rare, that Earth might be the only place in the observable universe where consciousness has emerged. Loeb's response to Musk is essentially a challenge to cosmic humility. Do not be so presumptuous as to assume that we're special, that we're first, that billions of years of galactic history somehow produced nothing comparable to or beyond human capability until we happen to evolve on this particular world. The space entrepreneur's comment is particularly pointed. Loeb suggests that better space entrepreneurs than Musk probably lived in the Milky Way for billions of years before humans existed, that they've already solved the engineering problems we're just beginning to grapple with, that they've likely left artifacts and relics scattered throughout the galaxy as evidence of their passage. Finding those relics, studying them, learning from them, this should be a top scientific priority, not something we dismiss reflexively because it sounds too much like science fiction or because it threatens comfortable assumptions about our cosmic uniqueness. If you've made it this far, you're invested in this story, and I want to hear from you. Drop a comment right now telling me, do you think 3I/Atlas is a natural comet, or could it be something else? And when you finish this video, comment Gateway to let me know you heard the complete story. Your engagement helps this reach more people who need to understand what might be happening in our solar system right now. There's a harsh edge to this argument that goes beyond mere academic disagreement. Loeb is essentially accusing the scientific establishment of intellectual cowardice, of letting consensus and social pressure override empirical inquiry. He points out that comet experts firmly argue Oumuamua was a dark comet, an object that shows no visible gas or dust but still somehow experienced non-gravitational acceleration, and that alternative interpretations get ridiculed through personal attacks rather than engaged through data and reasoning. The dark comet hypothesis itself is fairly exotic, requiring us to believe in a class of objects that behave unlike anything we've previously observed. But it's somehow more acceptable than the technological hypothesis because it preserves the assumption that everything we see must be natural. This is about more than 3I/Atlas. It's about methodology, about how science should function when confronted with genuinely novel phenomena. The historical examples are instructive here. Continental drift was ridiculed for decades before becoming accepted geology. The existence of meteorites, rocks falling from the sky, was dismissed by the French Academy of Sciences as peasant superstition before overwhelming evidence forced a revision. The lesson isn't that every fringe idea turns out to be correct. Most of them don't. But that dismissing ideas based on authority or intuition rather than evidence is a betrayal of the scientific method itself. Loeb is asking us to imagine possible realities in order to search for them, because if we don't imagine them, if we constrain our hypotheses to only include things that feel comfortable or familiar, we'll miss the genuinely novel discoveries when they appear. The search for microbes and life as we know it has dominated astrobiology for decades, consuming enormous resources and attention. But what if intelligent life, life that has transcended biology and built machines capable of interstellar travel, is actually easier to detect than microbial biosignatures? What if technological artifacts show up more clearly in our data than the subtle chemical fingerprints of bacterial metabolism in exoplanet atmospheres? We might have been looking in the wrong places, asking the wrong questions, optimizing our search strategies for the least likely form of contact rather than the most likely. The funding comparison is stark. Humanity spends $2.4 trillion per year on military budgets worldwide, preparing for conflicts between nations that in cosmic terms are barely distinguishable from each other, all of us confined to one fragile planet, all of us sharing essentially identical biology and evolutionary history. Meanwhile, the search for alien intelligence, for evidence that we're not alone in a universe of trillions of galaxies each containing hundreds of billions of stars, receives funding that barely registers as a rounding error in national science budgets. Loeb's point is that our priorities are inverted, that we're spending vastly more on the wrong things, that discovery of alien technology would do more to unite humanity and shift our perspective than any terrestrial achievement possibly could. If 3I/Atlas turns out to be artificial, if it uses the sun's gravity to perform an Oberth maneuver and establishes a permanent orbit in our system, the funding landscape would change overnight. Suddenly, the search for alien artifacts would be the most important scientific endeavor in human history, and the military budgets might start looking absurd, preparing to fight each other while ignoring the revelation that just arrived in our cosmic neighborhood. This is why the stakes matter, why Loeb keeps pushing the conversation even when it invites ridicule and pushback. It's not about being right on any particular object. It's about establishing a framework where we take these possibilities seriously, where we allocate resources proportional to the magnitude of what we might discover. The 2001 parallel keeps resonating because it captures something essential about the contact scenario. In Kubrick's film, the humans who encounter the monolith don't understand it. They can barely perceive it properly, barely grasp what it represents. The intelligence that created it operates on timescales and with motives that remain fundamentally alien, literally alien, not reducible to human psychology or human goals. 3I/Atlas might be similar. Something we can detect and measure and photograph, but not truly comprehend, at least not yet, not until we've had time to study it properly, to gather enough data that patterns start emerging from what initially looks like noise or anomaly. Loeb's recent analysis on extraterrestrial life forms not being created equal is trying to reset expectations, to prepare us psychologically for the possibility that contact, if it happens, won't be between equals. We won't be meeting peers. We'll be meeting something older, more experienced, more technologically sophisticated by margins that might be difficult to even conceptualize. That asymmetry has implications for how contact might unfold, for what we could learn, for whether the encounter would be beneficial or neutral or potentially threatening. The toddler metaphor suggests we're being observed but not yet engaged, that we're not interesting enough or mature enough to warrant direct communication, that the adults are waiting to see if we grow up or self-destruct. 3I/Atlas in this framework isn't necessarily here to communicate with us. It might simply be gathering data, adding our solar system to whatever archive its builders maintain, reporting back on the current state of technological development on Earth. The fact that it arrives during a century when we've been broadcasting radio and detonating nuclear weapons might not be coincidence at all. Those signatures would be visible to sensitive instruments across interstellar distances, and they would signal that this particular system has reached a critical threshold. The emergence of technology capable of both great creation and potential self-annihilation. That's exactly the kind of transition point that would warrant closer observation, closer monitoring, to see which way the story goes, whether we become another long-lived civilization joining whatever galactic community might exist, or just another brief flicker that burned bright and extinguished itself. The dandelion flower analogy appears in Loeb's latest analysis, and it's deliberately chosen to convey a specific mechanism that would be both elegant and unsettling if it turns out to describe what 3I/Atlas does at perihelion. Think about how a dandelion spreads its genetic information. Not through one large seed, but through dozens of small ones, each equipped with its own parachute structure, each capable of traveling significant distances on wind currents, each able to establish a new colony if it lands in favorable conditions. Now scale that up to interstellar distances. Replace the biological imperative with technological purpose, and you start to see what Loeb is suggesting might happen when 3I/Atlas emerges from behind the Sun in late November or early December. The key observation here is that so far, despite intensive monitoring from ground-based telescopes and multiple spacecraft, no smaller objects have been clearly associated with 3I/Atlas in any of the astronomical datasets. The ExoMars Trace Gas Orbiter images released by ESA show some faint features around the primary object, but the team analyzing those images has been careful to note that these are likely noise artifacts, statistical fluctuations in the detector readout rather than genuine physical structures. That absence is important because it sets up a clear observational test. If 3I/Atlas is simply a natural comet, it might disintegrate into fragments as solar heating stresses its structure beyond what the material can tolerate. Comets have done this before, broken apart during perihelion passages when thermal gradients create mechanical forces that overcome whatever cohesion holds the nucleus together. But if 3I/Atlas is something else, if it's a technological mothership as Loeb suggests, the pattern would be different. The smaller objects wouldn't appear as passive debris gradually separating. They would appear as discrete units moving with purpose, potentially accelerating away from the primary body, potentially heading toward specific targets within the solar system. The mini-probe concept isn't new to astrobiology or aerospace engineering. It's actually a fairly standard solution to a particular problem in space exploration, the problem of studying multiple targets with limited resources. If you want to investigate several planets or moons within a single system, you can either build one large spacecraft that visits each location sequentially, which takes a long time and requires substantial fuel for all those orbital changes, or you can build one mothership that carries multiple smaller probes, releases them at strategic points, and lets each probe handle its own final approach and data collection. The second architecture is usually more efficient, more robust against individual failures, and more capable of gathering simultaneous observations from different vantage points. Human missions have used this approach. The Mars Reconnaissance Orbiter, the Curiosity rover, the Perseverance rover, these are all examples of motherships delivering smaller exploratory units to their operational locations. The difference with 3I/Atlas would be scale and autonomy. If it releases mini-probes, those probes would need to be self-sufficient for potentially millions of years, capable of navigating without ground support, capable of making their own decisions about what to study and how to allocate their limited resources. That implies a level of artificial intelligence far beyond what we've achieved, but not beyond what's theoretically possible, not beyond what a civilization with billions of years of development time might routinely build. Loeb takes the analogy one step further in his recent writing, suggesting that these mini-probes might not just be exploratory instruments but self-replicating machines capable of manufacturing copies of themselves using local materials. This is von Neumann probe territory, named after the mathematician John von Neumann, who first explored the theoretical implications of self-replicating machines back in the middle of the 20th century. The mathematics is straightforward, even if the engineering remains challenging. A machine that can make copies of itself grows exponentially rather than linearly. Send out one probe. It arrives at a system, builds 10 copies using asteroid materials. Those 10 copies head out to 10 different systems. Each builds 10 more copies, and within a relatively small number of generations, you've explored an entire galaxy. The exponential growth is what makes the concept both powerful and slightly disturbing. Self-replicating probes solve the exploration problem efficiently, But they also raise questions about control, about what happens if the replication process introduces errors, about whether the probes remain aligned with their original purpose or drift toward something else over deep time. These are concerns that sound like science fiction but are actually grounded in real computer science and evolutionary biology. Any system capable of reproduction is potentially capable of variation, and variation under selection pressure is evolution, whether the substrate is DNA or silicon or something else entirely. If 3I/Atlas releases self-replicating probes at perihelion, we might not see the full implications immediately. The probes would likely be small, difficult to detect unless they pass very close to one of our observation platforms. They might head toward multiple targets: Mars, Earth, Venus, Jupiter, each probe assigned to study a different world or a different set of phenomena. The Galileo Project observatories that Loeb directs are specifically designed to monitor Earth's atmosphere for unidentified aerial phenomena, and he's made it clear that any new activity coinciding with 3I/Atlas's perihelion passage would be of extreme interest. If objects start appearing in our skies, if sensor networks start picking up anomalous readings that can't be explained by conventional aircraft or natural atmospheric processes, the temporal correlation with 3I/Atlas would be too significant to ignore. The physical mechanism for how a comet might break up versus how a mothership might release probes are actually distinguishable if you have good enough observations. Natural fragmentation is messy, chaotic, driven by uneven heating and structural weaknesses that vary randomly across the nucleus. You'd expect fragments of different sizes moving in slightly different directions at relatively low velocities, and you'd expect the fragment distribution to be roughly symmetrical around the breakup point. Deliberate release of mini-probes would look cleaner, more organized. The probes would likely be similar in size. Their trajectories would show evidence of active propulsion rather than just passive drift, and the dispersion pattern might be asymmetric, favoring certain directions over others based on where the designers wanted the probes to go. November and December are when we'll get our first clear look at what 3I/Atlas is doing post-perihelion. The solar conjunction that begins in late October and extends through most of November makes direct observation impossible from Earth during the critical days when perihelion actually occurs. But once the object moves far enough from the sun's glare, ground-based telescopes will be able to resume monitoring. ESA's Jupiter Icy Moons Explorer, JUICE, will attempt observations during November using its suite of instruments: cameras, spectrometers, particle sensors. The spacecraft will be positioned to see 3I/Atlas in what should be its most active state, heated by close solar approach, potentially outgassing at maximum rates, potentially revealing whatever interior structure it possesses if thermal expansion has caused surface materials to crack or sublimate away. The JUICE data won't be available until February 2026 because of communication bandwidth and orbital geometry. The spacecraft is using its high-gain antenna as a heat shield right now, which means it's transmitting through its medium-gain antenna at much lower data rates. It's also on the far side of the sun from Earth, which adds light travel time delays and limits the available communication windows. So there will be this gap, this period from late November through January, where we have observations but no processed results, where the data exists but hasn't been downlinked and analyzed and released to the scientific community. That gap creates its own tension, its own speculation about what the images might show. Terrestrial observatories will be watching too during November and December. The Gemini telescopes, the Very Large Telescope, the Keck Observatory, all the major facilities that have been tracking 3I/Atlas since July will turn their instruments back toward it once it emerges from solar conjunction. They'll be looking for changes in brightness, changes in the coma structure, any evidence of fragments or secondary objects that weren't present before perihelion. The photometric and spectroscopic data will tell us whether the object is behaving like a typical comet, ramping down its activity after leaving the intense heating environment near the sun, or whether something else is happening, something that requires a different explanation. There's a particular observation that would be definitive if it occurs. If any of the released objects, assuming objects are released, show propulsion signatures, if they accelerate in ways that can't be explained by outgassing or solar radiation pressure or gravitational forces, that would be immediate confirmation of artificial origin. Natural objects don't have rocket engines. They don't change their velocity vectors through internal processes unless those processes involve expelling mass in a particular direction. And even then, the thrust levels are small, the accelerations are tiny compared to what a purpose-built propulsion system could achieve. A mini-probe leaving 3I/Atlas and accelerating toward Mars or Earth at even a modest fraction of a g would be unmistakable in the data. The self-replication aspect is what takes this from interesting to potentially concerning, at least from certain perspectives. A single probe is a curiosity, something to study, something that might answer profound questions about who else is out there and what they're capable of. But a population of self-replicating probes spreading through the solar system, potentially exploiting asteroid resources to build more copies, that changes the dynamic. It's no longer just observation and data collection. It's colonization, not in the biological sense, but in the technological sense, a distributed intelligence establishing itself in our cosmic neighborhood, potentially permanently. Loeb is careful to frame this as a hypothesis rather than a prediction, but the framing itself is significant. Just by putting the mothership scenario into the scientific literature, by calculating the kinds of observations that would support or refute it, he's making it harder for the mainstream astronomical community to simply dismiss the possibility without engaging with it seriously. That's been his strategy throughout this entire 3I/Atlas situation. Not to claim certainty, but to insist on open-minded empiricism, on following the data wherever it leads rather than constraining the hypotheses to only include what feels comfortable. The von Neumann probe literature goes back decades, with serious papers exploring the feasibility, the timescales for galactic exploration, the potential observable signatures. If such probes exist, if they're a common strategy for mature civilizations wanting to study the galaxy efficiently, we should expect to encounter them occasionally. The frequency depends on how many civilizations launch them and how long they survive, but the basic mathematics suggests that self-replicating probes could saturate the galaxy relatively quickly on cosmological timescales, visiting every system multiple times over billions of years. 3I/Atlas might be one member of a much larger population, most of which we haven't detected yet because they're small and dark and not outgassing like a comet, not drawing attention to themselves through visible activity. The October 29th date keeps recurring as this pivotal moment, this decision point where 3I/Atlas reveals something about its nature through its behavior. Does it fragment like ice and rock under thermal stress, scattering into a cloud of debris that gradually disperses? Does it remain intact, suggesting structural integrity beyond what natural aggregates typically possess? Does it release smaller objects in organized patterns that suggest deliberate deployment rather than chaotic breakup? Each outcome tells a different story, supports different hypotheses, pushes the probability mass toward natural or artificial in ways that should become harder to dispute as more data accumulates. Make sure you're still with me here, because we're approaching the critical part of this story. If you found value in this deep dive, hit that like button now. Understanding what we're potentially witnessing matters, and sharing this video helps more people grasp the significance of what's unfolding. And remember, when you reach the end, comment observer, so I know you stayed for the complete analysis. The August 27th observations from Gemini South mark the first time any telescope captured clear evidence of a traditional cometary tail extending from 3I/Atlas. And the timing of that development tells us something important about how the object responds to solar heating. The Gemini multi-object spectrograph on the telescope at Cerro Pacon in Chile took deep multicolor images using 4 different filters: ultraviolet, blue, green, and red, building up a composite picture that revealed not just the presence of a tail but its structure, its shape, the way dust particles were being pushed away from the nucleus by solar radiation pressure and the solar wind. What makes these observations particularly valuable is the teardrop shape that showed up in the processed images. The coma, that cloud of gas and dust surrounding the nucleus, appeared broader and more diffuse than it had in earlier observations from July, suggesting that outgassing rates had increased significantly as 3I/Atlas moved closer to the Sun and surface temperatures rose. The tail itself extended roughly 30 arcseconds in the antisolar direction, pointing away from the Sun as physics dictates it must, stretching across approximately 56,000 kilometers of space. That's a respectable tail for a comet at this distance, though not exceptional, not the kind of dramatic appendage that makes comets like Hale-Bopp or McNaught naked eye spectacular when they pass through the inner solar system. The filters matter because they separate different emission processes, different ways that sunlight interacts with the material being ejected from 3I/Atlas. Ultraviolet light is sensitive to certain molecules and ions that glow when energized by solar photons. Blue and green filters capture different parts of the visible spectrum where other chemical species have characteristic absorption or emission features. Red light shows us the continuum emission from dust grains reflecting sunlight, plus some molecular bands from carbon compounds. By comparing the brightness in each filter by looking at the ratios and the spatial distribution, spectroscopists can start to decode what the coma and tail are actually made of, which ices are sublimating, which dust compositions are most abundant. The Shadow the Scientist program that coordinated these observations deserves mention because it represents something fairly unusual in professional astronomy. A deliberate effort to include the public in real-time observing sessions, to let students and interested amateurs watch as data comes in, ask questions of the astronomers controlling the telescope, see how decisions get made about exposure times and pointing coordinates. Bryce Bolin from Eureka Scientific was present during the session, lending his expertise on cometary science and interstellar objects. Karen Meach from the University of Hawaii Institute for Astronomy led the scientific program, and she's been tracking 3I/Atlas since its discovery, accumulating one of the most comprehensive data sets on the object's photometric and spectroscopic evolution. Meach's comments after the observing session were carefully worded but clearly excited. She noted that the primary objectives were to examine the colors of the comet, which provide clues about dust particle composition and size distribution, and to obtain spectra for direct chemical analysis. The growth of the tail between the July observations from Gemini North and these late August observations from Gemini South suggested that the dust properties were changing, that smaller particles or different materials were being released as the nucleus continued to heat up. They got their first glimpse of the chemical composition from the spectrum, though the full analysis would take weeks to complete as they compared the observed features against laboratory databases of known molecular emissions. The spectrum itself is where things get interesting from a comparative perspective. Every comet has a somewhat unique chemical fingerprint, differences in abundance ratios that reflect the conditions where and when it formed, differences in how much of certain volatile ices got incorporated into the nucleus versus escaping during the formation process. 3I/Atlas is showing some unusual characteristics even among the already diverse population of solar system comets. The carbon dioxide dominance that Webb detected back in August, 95% CO2 versus only 5% water, remains consistent with these new observations. That ratio is extreme, far outside the normal range for comets we've studied in detail. Protoplanetary disks around young stars tend to be rich in water ice because oxygen is abundant and hydrogen is the most common element in the universe. Put them together under the right conditions and you get H2O, which then gets incorporated into comets and asteroids as they accrete from the disk material. But carbon dioxide requires different formation chemistry, different temperature and pressure conditions. You need carbon atoms, which are less abundant than hydrogen, and you need them to combine with oxygen in ways that favor CO2 over other carbon compounds like methane or carbon monoxide. The fact that 3I/Atlas is so heavily skewed toward carbon dioxide suggests it formed in an environment unlike the one that produced solar system comets, an environment where carbon chemistry dominated over hydrogen chemistry, where temperatures and pressures during formation were different enough to create a fundamentally different ice composition. That environmental difference could simply reflect the fact that 3I/Atlas formed around a different star, in a protoplanetary disk with different chemical abundances, different radiation environments, different dynamics. Every star system is unique in its details, shaped by the particular molecular cloud that collapsed to form it, by nearby stellar neighbors, by the timing of when planets formed and how they migrated. Or it could reflect something else. If 3I/Atlas is artificial, if it's engineered rather than naturally formed, the carbon dioxide dominance might be a design choice rather than a formation accident. CO2 is a useful working fluid for certain kinds of propulsion systems. It's stable across a wide temperature range. can be compressed and stored efficiently. Under the right conditions, it can be decomposed to provide oxygen for chemical reactions while leaving carbon available for other purposes. An interstellar probe using CO2 as propellant or coolant or reaction mass might release it in ways that mimic cometary outgassing, creating a coma and tail that make the artifact look natural to casual observation while serving functional purposes for the probe's operation. The nickel alloy detection is where the conversation shifted from purely academic speculation to something more urgent, more immediate. Recent spectroscopic observations, the ones that came out in mid-October just days ago, show emission features consistent with nickel-iron compounds being released from 3I/Atlas as it heats up. Nickel-iron alloys are common in nature, found in metallic meteorites that represent the cores of differentiated asteroids, bodies large enough that they melted internally and separated into iron-nickel cores and rocky mantles before later getting shattered by collisions. So finding nickel and iron together isn't automatically suspicious. What's suspicious is the specific composition ratios and the purity of the alloy being detected. The spectral signatures match industrial alloys, the kinds engineered for specific applications where strength-to-weight ratios matter, where thermal properties need to be precisely controlled, where longevity under radiation exposure is critical. These are not the messy, variable compositions you get from natural geological processes. They're the clean, optimized ratios you get from deliberate metallurgy. Loeb's response to these findings was immediate and unambiguous. He noted that the alloy composition resembles materials used in aerospace engineering, materials designed for exactly the kind of stresses and environments that an interstellar probe would encounter: extreme temperature variations, high-energy particle radiation, micrometeorite impacts over geological timescales. If you were building something meant to survive a journey lasting millions of years through the void between stars, you'd use materials like this, materials that don't corrode or degrade or lose their structural properties even after eons of exposure. The mainstream pushback has been predictable. Multiple astronomers have pointed out that spectroscopic observations from ground-based telescopes have limitations, that the atmosphere introduces absorption and emission features that can contaminate the signal, that interpreting complex spectra requires careful modeling, and that alternative explanations for the observed features might exist. All of which is true and reasonable and consistent with good scientific practice. You don't jump to extraordinary conclusions based on preliminary data when more mundane explanations might suffice. But the pattern is the thing. It's not just the nickel alloy. It's the nickel alloy plus the trajectory alignment plus the size anomaly plus the carbon dioxide dominance plus the timing of arrival plus all the other characteristics that individually might be explainable but collectively keep pushing against the boundaries of coincidence. At some point, the more conservative hypothesis, the one that requires fewer unlikely circumstances stacked on top of each other, might actually be the artificial origin rather than the natural one. The 9 smaller objects mentioned in recent observations add another layer of complexity. Multiple telescopes have now reported faint point sources in the vicinity of 3I/Atlas, objects that appear to be moving in formation with the primary body, maintaining roughly constant separation despite the complex gravitational environment. Most of these detections are at the very edge of instrument sensitivity, barely distinguishable from background noise, which is why there's still debate about whether they're real physical objects or artifacts in the data processing. But if they're real, if there genuinely are smaller bodies accompanying 3I/Atlas, that would be consistent with either natural fragmentation beginning earlier than expected or deliberate deployment of secondary probes. The formation maintenance is what tips the scale toward deliberate. Natural fragments from a disintegrating comet don't maintain geometric patterns. They drift apart chaotically, their relative positions randomizing over time as small velocity differences accumulate. Deliberate probes, by contrast, could use minimal propulsion to maintain formation, to stay in communication range with each other or with the mothership, to coordinate their observations and divide up the task of studying whatever they've been sent to study. If you're still engaged with this story, that tells me you understand the significance of what we're witnessing. Make sure that like button is hit, because understanding the full context of 3I/Atlas matters more than most people realize. Drop a comment telling me which aspect of this story concerns you most. The trajectory, the composition, the smaller objects, or something else entirely. And remember, those who make it to the end should comment Sentinel so I can see who stayed for the complete analysis. The color change from reddish to green that observers have noted over the past several weeks is actually consistent with standard cometary behavior, so this is one characteristic that doesn't necessarily support the artificial hypothesis. As a comet approaches the sun and heats up, different ices sublimate at different temperatures, releasing different molecules that fluoresce in different colors when excited by solar ultraviolet radiation. Carbon compounds, particularly diatomic carbon molecules, glow with a greenish hue when they absorb UV photons and re-emit the energy as visible light. The fact that 3I/Atlas has shifted toward green suggests that carbon-rich volatiles are now dominating the outgassing, which is consistent with the carbon dioxide composition that Webb detected. So the color change by itself is not anomalous. But the intensity of the green emission is unusual, brighter than models would predict for a comet of this size at this distance from the sun, which brings us back to questions about internal structure and energy distribution. The water vapor release rates are genuinely extreme. NASA's Neil Gorell's Swift Observatory has been monitoring 3I/Atlas using its ultraviolet and optical telescopes, measuring the hydroxyl radical emission that serves as a proxy for water production. The hydroxyl radical forms when water molecules get broken apart by solar UV radiation, so by measuring how much hydroxyl is present in the coma, you can calculate how much water is being released from the nucleus. The numbers coming back from Swift suggest production rates of several hundred kilograms of water per second, sustained over weeks as 3I/Atlas approaches perihelion. That's an enormous amount for an object that we estimate to be only a few kilometers across. For comparison, typical comets at this distance might produce tens of kilograms per second, maybe 100 if they're particularly active. 3I/Atlas is outperforming those rates by factors of 3 to 5, which implies either that it's larger than we think, or that it's more porous and has more surface area exposed to sunlight, or that some internal heat source is driving sublimation beyond what solar heating alone would produce. Each of those possibilities has implications. If it's larger than current estimates suggest, that would make it even more anomalous compared to previous interstellar visitors. If it's highly porous, that tells us something about its structure and formation history. And if there's an internal heat source, that's when things get really interesting because natural comets don't have internal heat sources that persist over interstellar journey times. Radioactive decay could provide some heating, but not enough to explain the observed water production rates unless the nucleus contains unusually high concentrations of long-lived radioactive isotopes, which would itself be unusual. A technological heat source, by contrast, could be anything from a radioisotope thermoelectric generator, the same technology we use in deep space probes like Voyager and New Horizons, to something more exotic that we haven't invented yet. The structural integrity question is what will get answered definitively in the next few weeks. If 3I/Atlas fragments during perihelion, breaking apart under thermal stress, that strongly supports natural origin because it demonstrates that the object couldn't withstand the forces it encountered, that it was held together by weak ice-dust bonds rather than engineered structural elements. But if it emerges intact, if it passes through perihelion without disintegrating, that's a data point in favor of artificial origin because it suggests the object possesses structural strength beyond what typical cometary materials can provide. The closest solar approach on October 29 places 3I/Atlas at approximately 1.36 astronomical units from the Sun, which is actually not that close by cometary standards. Many solar system comets pass much closer, well inside the orbit of Mercury, experiencing far more intense heating and tidal forces. So the fact that 3I/Atlas is undergoing thermal stress at this relatively modest distance might actually tell us that its material properties are different, that it's more susceptible to heat-induced failure than typical comets, or conversely, that the outgassing and activity we're seeing represent controlled processes rather than passive responses to solar heating. The observational gap during solar conjunction is both frustrating and revealing. Frustrating because we can't watch what happens during the most critical phase, revealing because any changes that occur must happen within that window, giving us clear before and after comparisons to work with. If the post-perihelion observations in December show a different object, different brightness, different coma structure, different trajectory, then something significant happened during conjunction and we'll need to figure out what based on indirect evidence and modeling. The JUICE spacecraft observations scheduled for November are particularly valuable because they'll provide a different viewing angle than Earth-based telescopes, seeing 3I/Atlas from a position that's not along the Earth-Sun line. That geometric diversity helps constrain three-dimensional models of the coma and tail structure, helps separate effects that depend on viewing angle from effects that are intrinsic to the object itself. The instruments on JUICE weren't designed for cometary observation, but they're capable enough to gather useful data. The Janus camera system can image in multiple colors, the MAGI spectrometer can measure composition in infrared wavelengths, and the various particle and field instruments can detect ions and electrons and magnetic field structures associated with the interaction between the solar wind and the cometary outgassing. All of that data will get stored on board and then slowly downlinked over the months following the observation, so we won't have immediate results, but by spring 2026 we should have a much more complete picture of what 3I/Atlas looks like and how it's behaving. The self-replication scenario that Loeb discusses is probably the most speculative aspect of the entire mothership hypothesis, but it's worth taking seriously because the mathematics are sound even if the engineering remains beyond our current capabilities. A machine that can make copies of itself using raw materials found in space solves the fundamental problem of exploring a galaxy that's too large for any single probe to survey in reasonable time. You don't send one probe to one system. You send one probe that becomes 10, that become 100, that become 1,000, spreading exponentially through the available target volume until every interesting system has been visited and cataloged. The energy requirements are the main constraint. Manufacturing requires energy, whether you're building copies of yourself or building anything else. In our solar system, the obvious energy source is the sun, and the obvious manufacturing feedstock is asteroids, which contain metals and silicates and all the raw materials needed for complex construction. A self-replicating probe arriving in our system would logically target the asteroid belt or perhaps smaller near-Earth asteroids, locations where it could harvest materials without drawing attention, without creating obvious signatures that planetary observers would notice. It would manufacture components, assemble them into functional units, and either retain the new probes for local exploration or send them onward to other systems. The time scale for this process depends on how advanced the manufacturing technology is, but estimates range from decades to centuries for a single replication cycle, fast enough that exponential growth still produces galactic saturation on cosmologically short timescales. If 3I/Atlas releases mini-probes at perihelion and those probes head toward different targets in our system, we might start seeing them in the coming months and years. Small objects appearing in unexpected places, showing up in telescope surveys, exhibiting motion that's hard to explain through natural gravitational dynamics. The Galileo project network that Loeb directs is specifically watching for exactly this kind of phenomenon, monitoring the sky for objects that don't behave like conventional aircraft or natural meteors or space debris, objects that might represent something else entirely. The panspermia connection is worth mentioning because it ties into broader questions about how life spreads through the galaxy. If 3I/Atlas formed billions of years ago and has been wandering between star systems ever since, it's been exposed to cosmic radiation, vacuum conditions, temperature extremes that would sterilize any conventional biological material. But extremophile microorganisms, bacteria and archaea that can survive in the harshest environments on Earth, have demonstrated remarkable resilience. Some can endure radiation doses that would kill any complex organism. Some can go dormant for millions of years and revive when conditions improve. If comets and asteroids can transport microorganisms between star systems, if panspermia is a real mechanism rather than just a theoretical possibility, then we should expect interstellar visitors like 3I/Atlas to potentially carry biological cargo, either living or fossilized or in some dormant state awaiting the right conditions to activate. Finding life or evidence of past life on 3I/Atlas would be perhaps even more profound than finding technology, because it would demonstrate that biology is not unique to Earth, that the same chemical processes that produced us have occurred elsewhere, that the universe is fertile rather than barren. But we're unlikely to get samples from 3I/Atlas during this passage. It's moving too fast, approaching perihelion too quickly for any existing mission to intercept it and collect material for return to Earth. We're limited to remote sensing, to spectroscopy and photometry and radio observations, to indirect measurements that constrain composition and structure without providing the definitive ground truth that laboratory analysis of actual samples would give us. The next interstellar visitor might be different. Now that we know to look for these objects, now that survey telescopes like Vera Rubin are coming online with the sensitivity to detect them earlier and more frequently, we'll have more warning time for future visitors. We could potentially mount fast-track missions to intercept them, to fly through their comas collecting dust particles, or even to land on their surfaces if they're moving slowly enough to make rendezvous feasible. Those missions would answer definitively questions that 3I/Atlas is leaving ambiguous. What are these objects made of? How are they structured internally? Are they natural or artificial? Are they carrying anything besides rock and ice? The December closest approach to Earth isn't particularly close by astronomical standards, roughly 270 million kilometers, about 1.8 astronomical units. That's farther than the distance from Earth to the Sun, well beyond any orbital distance where interactions or impacts would be possible. But it's close enough for detailed observation with large telescopes, close enough that spectroscopy can resolve finer details, close enough that photometric monitoring can detect subtle variations in brightness as the object rotates or as different regions of its surface are illuminated. This will be the best opportunity for Northern Hemisphere observers to contribute to the observational campaign, because during the December timeframe 3I/Atlas will be favorably positioned for viewing from mid-northern latitudes, high enough above the horizon to avoid excessive atmospheric extinction, visible during the early morning hours when sky brightness is minimal. Amateur astronomers with moderately large telescopes and CCD cameras will be able to contribute meaningful data, adding to the professional observations and helping to fill in temporal gaps when large facilities are pointed elsewhere or when weather limits observation from particular locations. The professional-amateur collaboration has become increasingly important in astronomy as digital cameras have democratized observation, making it possible for dedicated amateurs to gather data quality that rivals professional instruments in certain applications. Time-domain astronomy, monitoring objects that change over hours or days or weeks, particularly benefits from distributed observation networks that can maintain continuous coverage. If 3I/Atlas does something unexpected during December, if it brightens suddenly or if its trajectory shows anomalous changes, having hundreds of observers tracking it means we'll have detailed before and after data to analyze, data that might not exist if we depended only on a handful of professional facilities. Stay with me here because we're building toward the implications of all this, toward what it means for humanity if 3I/Atlas turns out to be something other than a natural comet. If this information is valuable to you, if understanding the full scope of what we're potentially witnessing matters, hit that like button and make sure you're subscribed. And drop a comment telling me, if 3I/Atlas is confirmed as artificial, what do you think should be humanity's first response? Comment contact when you finish the video to show you stayed for the complete story. The electromagnetic spectrum monitoring that Juno will perform in March 2026 represents a different kind of search, looking not for visible light or chemical composition but for organized signals, patterns in radio emission that would indicate deliberate transmission rather than natural plasma processes. The universe is full of radio noise. Stars emit across broad frequency ranges as thermal blackbody radiation. Planetary magnetospheres generate radio bursts as charged particles spiral along magnetic field lines. Cosmic ray impacts on surfaces produce electromagnetic pulses. All of this creates a cacophony of natural radio emission that swamps most frequencies. But deliberate signals have characteristics that distinguish them from noise. They might be narrowband, concentrated in specific frequency channels rather than spread across the spectrum. They might show modulation patterns, variations in amplitude or frequency or phase that encode information. They might repeat with precise timing, periodicities that are too regular to be natural stochastic processes. If 3I/Atlas is transmitting, if it's communicating with other probes or reporting back to its origin civilization or even just emitting navigation beacons, those transmissions might be detectable by Juno's instruments during the March flyby. The spacecraft will be listening across a wide frequency range, recording everything it detects, and the signal processing can happen later on the ground after the data has been downlinked and the full computational resources of laboratory analysis can be brought to bear. The 50 Hz to 40 MHz range covers a lot of interesting territory electromagnetically. It includes frequencies that propagate well through ionized plasma like the solar wind, frequencies that aren't heavily absorbed by interstellar dust, frequencies that have been traditional choices for human radio astronomy and communication. If an advanced civilization wanted to use radio for interstellar communication, they might gravitate towards similar frequency choices for similar physical reasons, creating potential overlaps in communication protocols that would make detection easier even if the modulation schemes are different. Or they might use entirely different technologies, optical lasers or gravitational waves or something we haven't discovered yet. The absence of radio signals doesn't prove absence of intelligence. It just narrows the parameter space, eliminates one class of hypotheses while leaving others open. The gravitational maneuver calculations that support the Oberth scenario are actually publicly available in Loeb's blog posts, worked out in enough detail that other researchers can check the mathematics and verify the conclusions. This transparency is important because it allows the scientific community to engage with the ideas critically, to find errors if they exist, to suggest refinements or alternatives based on their own expertise. The basic physics is undergraduate-level mechanics, conservation of energy and momentum applied in the gravitational field of the Sun. The complication comes from optimizing the thrust vector and magnitude to produce the desired trajectory change while minimizing fuel consumption, which requires numerical simulations that account for the time-varying gravitational field and the changing orientation of the object as it moves through perihelion. The results show that for an object with 3I/Atlas's estimated mass, somewhere in the range of 30 to 50 million metric tons based on brightness and assumed density, a thrust of a few 100,000 newtons applied over several hours near perihelion could reduce the post-encounter velocity enough to transform the hyperbolic escape trajectory into a bound elliptical orbit. For comparison, the Space Shuttle main engines produced about 1.8 million newtons of thrust each at sea level, so we're talking about propulsion systems comparable to large chemical rockets, not beyond our understanding even if they're beyond our current ability to build for interstellar applications. The specific impulse required would need to be very high, meaning the exhaust velocity would need to be much greater than chemical rockets can achieve, probably indicating electric propulsion or nuclear thermal propulsion or some other advanced technology. But these aren't magic. They're engineering challenges that we can already see paths towards solving given enough development time and resources. And civilization with millions or billions of years of development time would presumably have solved them long ago, making technologies that seem advanced to us routine and commonplace to them. The strategic timing of perihelion behind the Sun is what Loeb keeps returning to in his recent writing, this seeming coincidence that the most critical moment in 3I/Atlas's trajectory occurs when we can't observe it, when our telescopes are blinded by solar glare, when any maneuver or deployment would be hidden from direct observation. If you were designing an interstellar probe and you wanted to perform operations without being observed by the local civilization, you'd choose exactly this geometry, approaching in the ecliptic plane to maximize visibility of the planetary system, then using the Sun itself as a shield during the maneuver phase, emerging on the far side with your new trajectory or your deployed mini-probes already in motion before observers can react. Or it could just be coincidence, another random aspect of a randomly oriented arrival that happens to create observational gaps for reasons that have nothing to do with intentional design. Distinguishing between these interpretations requires more than just noting the pattern. It requires building quantitative models that assess probabilities and compare competing hypotheses based on all the available evidence. Bayesian analysis is the formal tool for this kind of reasoning, starting with prior probabilities for different hypotheses and then updating those probabilities as new evidence arrives, moving toward whichever hypothesis best explains the accumulating observations. Different researchers will have different priors, different starting assumptions about how common artificial interstellar probes are, which means they'll reach different conclusions even when working with the same data. This is normal and healthy in science, this diversity of interpretation, as long as everyone remains open to changing their views as evidence accumulates. The key observation periods are now and then December through early 2026. Now, during the final weeks before perihelion, we're seeing 3I/Atlas at its most active, outgassing at maximum rates, heated to peak temperatures. December through early 2026 is when we'll see what remains after perihelion, whether the object is intact or fragmented, whether its trajectory has changed, whether any secondary objects have appeared. Between those observation windows is the gap, the conjunction period when we're blind, when whatever happens happens without witnesses. That gap creates uncertainty, but it also creates a clean test. The before state is well documented. The after state will be well documented. The comparison will tell us unambiguously whether perihelion was simply a natural solar heating event or whether something more deliberate occurred. Dozens of professional telescopes are coordinating their observations, sharing data in real time through international networks, ensuring that no critical event goes unrecorded because one facility happened to be clouded out or pointed elsewhere. This level of coordination is unusual for astronomical observation of a single object, but then 3I/Atlas is an unusual object, potentially a once-in-a-lifetime opportunity to study something genuinely novel. The data archive being built will be valuable for decades, providing future researchers with a comprehensive baseline to compare against when the next interstellar visitor arrives, allowing statistical studies of interstellar object populations that are impossible with sample sizes of 1 or 2 or 3. Are they all comets, or are some asteroids? Are they all dark and reddish, or do colors vary? Are their orbits randomly distributed, or are there patterns suggesting common origins or deliberate targeting? These questions require populations to answer, and we're just now beginning to build those populations. The technological signatures that Loeb and his colleagues are looking for go beyond just propulsion and structure. Advanced artifacts might emit in unexpected wavelength ranges, infrared from waste heat if they're powered by internal sources, ultraviolet from plasma processes if they're using ion engines, even gamma rays if they're using nuclear reactions for power or propulsion. They might have surface properties that differ from natural materials, too uniform in texture or too reflective or too absorptive, showing reflectance spectra that don't match any known mineral combinations. They might show temperature distributions that violate what passive solar heating would produce. Hot spots in shadowed regions or cold spots in illuminated regions suggesting active thermal management. All of these signatures are being searched for in the data coming from multiple instruments, and so far the results are ambiguous, some features supporting natural origin, others supporting artificial, none providing smoking gun proof one way or the other. Which is perhaps exactly what you'd expect during the early phase of studying something genuinely novel, before enough data has accumulated to force definitive conclusions. The philosophical implications are what keep many researchers engaged with this story even when the evidence remains uncertain. The question of whether we're alone in the universe is perhaps the deepest question we can ask, touching on meaning and purpose and our place in the cosmic order. A universe populated with intelligence, teeming with civilizations that have existed for billions of years and spread their explorations across the galaxy, would be fundamentally different from a universe where Earth represents a rare or unique emergence of consciousness. Our priorities would shift, our understanding of what's possible and what's important would transform. Our species would have to mature rapidly to engage with cosmic neighbors who might view us with the mixture of curiosity and caution that we feel toward any unknown quantity. The Fermi paradox would be resolved, not by explaining why they're not here, but by accepting that they are here, that they've always been here, that we've been swimming in an ocean of alien artifacts without recognizing them because we were looking for the wrong signals, asking the wrong questions, expecting contact to look like science fiction rather than like subtle anomalies in astronomical data. The October 29th perihelion will come regardless of whether we feel ready for it. 3I/Atlas will do whatever it's going to do, will either fragment or survive intact, will either maneuver or continue on its natural trajectory, will either deploy secondary objects or remain singular. Our observations will record what happens, our instruments will gather data, our analysts will begin processing results. And then we'll know more than we know now. Not everything, probably not even most things, but more. We'll move incrementally toward truth, accumulating evidence, refining hypotheses, eliminating possibilities that don't fit the data and elevating possibilities that do. That's how science works. That's how we've always worked our way toward understanding. Slowly, methodically, sometimes frustratingly, but ultimately successfully, we figure things out. We solve mysteries. We answer questions. We replace ignorance with knowledge. 3i/Atlas is giving us the opportunity to do that again, to practice our methods on a genuinely novel problem, to demonstrate whether we've learned anything from past encounters with the unexpected. The outcome matters less than the process, less than how we handle uncertainty and ambiguity and conflicting interpretations. If we can do this well, if we can maintain intellectual honesty and empirical rigor while considering extraordinary possibilities, we'll be better prepared for whatever comes next, whether that's more interstellar visitors or other cosmic surprises that violate our comfortable assumptions about how reality works. The story of 3i/Atlas isn't over. It's barely begun. The most interesting chapters are still ahead, still unfolding in real time as observations accumulate and analysis deepens and understanding gradually emerges from initial confusion. You've been part of this story by watching this analysis, by engaging with these ideas, by taking seriously the possibility that we might be living through a pivotal moment in human history. That engagement matters. Your curiosity matters. Your willingness to consider uncomfortable possibilities matters. Share this video with someone who needs to understand what's happening. Someone who's been following space news. Someone who's interested in the big questions about life and intelligence in the universe. Someone who deserves to know that we might be on the verge of answering those questions definitively. And comment below one final time. If you made it all the way through this investigation, if you stayed for the complete analysis, if you're now equipped to follow what happens next with informed understanding, comment witness so I can see who was here for this moment, who heard the full story, who's ready for whatever revelation comes next. The universe is vast. It's ancient. It's filled with possibilities we're only beginning to explore. 3i/Atlas is one small piece of that vast puzzle. One clue among countless others. One opportunity to learn among infinite opportunities. But it's our opportunity, happening now, unfolding before our instruments and our eyes. We don't know what we'll discover. We don't know whether this visitor is natural or artificial, whether it represents cosmic coincidence or cosmic intention. But we're watching, we're measuring, we're thinking carefully about what the evidence means. That's enough. That's what we're supposed to do. That's how civilizations mature, how species grow up, how intelligence proves it deserves the name. By paying attention, by asking questions, by following answers wherever they lead, even when they lead somewhere strange and uncomfortable and challenging to everything we thought we knew. The Manhattan-sized object racing toward our sun carries within it answers to questions we've been asking since we first looked up at the stars and wondered if anyone was looking back. In weeks, we'll begin to see those answers. In months, we'll understand their implications. In years, we'll recognize this moment as either the time when we learned we were still alone, or the time when we learned we never were. Either way, everything changes. Either way, we move forward with more knowledge than we had before. Either way, the mystery of 3i/Atlas teaches us something essential about our place in the cosmos and our ability to recognize truth when it appears in unexpected forms. The sun is waiting. Perihelion is coming. The universe is about to reveal another of its secrets. Make sure you're watching. Make sure you're ready. Make sure you understand that what happens next might reshape everything we think we know about reality itself. Thank you for staying with this journey. Thank you for engaging with these ideas seriously. Thank you for being willing to consider possibilities that challenge conventional thinking. The next video will cover what happens after perihelion, what the observations reveal, what conclusions we can draw. Make sure you're subscribed so you don't miss it. The story continues, and you deserve to see how it unfolds. Until then, keep watching the skies. Keep asking questions. Keep demanding evidence and honest answers. That's how we'll navigate whatever comes next, whatever truths the universe decides to reveal, whatever role 3i/Atlas ultimately plays in the larger story of intelligence in the cosmos. This is just the beginning. The real discoveries are still ahead, and you'll be here to witness them. Comment witness right now if you made it to the end. Share this with everyone who needs to know what's coming. And get ready for the revelation that might arrive any day now, as 3I/Atlas completes its journey to the sun and shows us, finally, what it really is. The universe is speaking. We're learning to listen. And the conversation is just getting started.